Hold your smartphone. Feel its smooth, cool surface. Tap the screen. A universe of information awakens at your touch. Have you ever wondered what makes that possible? It's not magic. It's not just clever coding or engineering. It's materials. Specifically, a family of 17 obscure elements on the periodic table known as rare earths. They are the invisible, unsung heroes behind the vibrant glow of your screen, the precise vibration of its haptic feedback, and the powerful tiny magnets in its speakers. Without them, the sleek device in your hand would be a lifeless brick, a ghost of its potential. These elements are the secret ingredient, the pinch of stardust that animates our modern existence. Think about the last time you listened to music through high-quality earbuds. The crisp, clear sound is delivered by incredibly strong, lightweight magnets. Those magnets are made with neodymium, a rare earth element. Consider the electric car silently gliding down the street, a beacon of our green energy aspirations. Its powerful, efficient motor relies on terbium and dysprosium to function under extreme heat without losing its magnetic force. These elements are not merely components, they are enablers. They are the fundamental building blocks that have unlocked a technological revolution. A revolution so profound and pervasive that we often forget to question its foundations. We take for granted a world that would be utterly unrecognizable without them. Even our health and well-being are deeply intertwined with these mysterious metals. When you undergo an MRI scan, the machine's powerful magnetic field, which allows doctors to see inside your body with astonishing clarity, is generated by superconducting magnets cooled to near absolute zero. But the contrast agent injected into your veins to make the images sharper? That contains gadolinium, another member of the rare earth family. From the precision-guided lasers used in modern surgery to the portable X-ray machines that save lives in remote locations, these elements are silent partners in our quest for longer, healthier lives. So, here we are, living in a world built on materials most of us have never heard of. A world where our most advanced technologies, from the trivial to the life-saving, are completely dependent on a handful of elements dug from the Earth's crust. They are the new oil. Not because we burn them for energy, but because they fuel our progress, power our ambitions, and now define the new frontiers of global power and competition. The story of rare earths is the story of our time, a tale of geology, chemistry, and human ingenuity colliding on a planetary scale. It's a story we all need to understand. What exactly are these rare earths? The name is a bit of a misnomer. They aren't all that rare, geologically speaking. Some, like cerium, are more abundant in the Earth's crust than copper or lead. The group consists of 17 elements, the 15 lanthanides plus scandium and yttrium, which are found in the same ore deposits and share similar chemical properties. Their real challenge, the source of their value and the drama surrounding them, lies not in their scarcity, but in their devilish difficulty. They are chemically sticky, clinging together in mineral deposits, making them incredibly hard and expensive to separate into their pure, usable forms. It's like trying to unscramble an egg, but on a molecular level. These elements are the chameleons of the periodic table, each possessing unique magnetic, luminescent, and catalytic properties that no other material can replicate. Europium, for instance, burns with a brilliant red light, which is why it was essential for the old CRT television screens, and is still used today to create the red pixels in your LED displays. Add terbium for green, and you have the foundation of a full-color digital world. Neodymium and samarium form the basis of the most powerful permanent magnets known to science. Magnets that are orders of magnitude stronger than the simple iron ones you remember from school. This is where their power truly lies, in their extraordinary, almost alchemical abilities. Let's journey from the everyday to the extraordinary. The hard drive storing your family photos uses a thin film of a rare earth alloy on its platters to hold magnetic data. The catalytic converter in your car uses cerium and lanthanum to scrub harmful pollutants from the exhaust, making the air we breathe cleaner. But their influence extends far beyond our civilian lives. Consider a modern F-35 fighter jet. It is a symphony of advanced technology, and nearly half a ton of rare earth elements are woven into its very being. They are in the radar systems, the electronic warfare suites, the guidance fins of its missiles, and the powerful electric motor that starts its engine. Without rare earths, our most advanced defense systems would be grounded. The precision of a smart bomb, the stealth of a modern submarine, the communications array of a satellite, all depend on these 17 elements. They amplify our senses, extend our reach, and sharpen our aim. They are not just enhancing our technology, they are defining the very limits of what is possible. They are the difference between a blunt instrument and a surgical tool, both in a hospital and on a battlefield. The quest to master these elements is a quest to master the physical world itself. How did one nation come to dominate the supply of these critical materials? The story of China's rise to rare earth supremacy is a masterclass in long-term strategic planning, economic foresight, and brutal industrial efficiency. It began decades ago, not with a bang, but with a quiet, calculated vision. In the 1980s, while the rest of the world saw rare earths as a niche, low-margin mining curiosity, Chinese leaders saw the future. Deng Xiaoping, the architect of modern China, famously declared in 1992, "The Middle East has oil, China has rare earths." This wasn't just a boast, it was a statement of intent, a strategic directive that would reshape global supply chains for a generation. China began by leveraging its vast, rich deposits, particularly the massive Bayan Obo mine in Inner Mongolia. But its strategy was multi-pronged. It invested heavily in the complex and dirty science of processing and refining these elements, a field that many Western countries were abandoning due to high costs and tightening environmental regulations. China was willing to pay the environmental price, viewing the pollution as a necessary cost of securing a strategic advantage. It subsidized its fledgling rare earth industries, allowing them to flood the global market with astonishingly cheap products, undercutting and ultimately bankrupting competitors from the United States to Australia. The world, enjoying the low prices, effectively outsourced its supply chain. The Molycorp mine at Mountain Pass, California, once the world's leading producer, was shuttered in 2002, unable to compete. The expertise, the equipment, the intellectual capital, it all withered away in the West, while it flourished in China. By the early 2000s, China wasn't just the world's leading miner of rare earths. It controlled over 95% of the global refined supply. It had achieved a near monopoly, not just on the raw materials, but on the entire technological ecosystem required to turn them into the high-purity metals and alloys that modern industry demands. The dragon wasn't just sitting on a hoard of treasure, it had built the only forge capable of shaping it. The first major shockwave came in 2010. Following a maritime dispute, China halted rare earth shipments to Japan, a technological powerhouse utterly dependent on them. The message was clear and sent a panic through global markets and government halls. Prices for some elements skyrocketed by thousands of %. Suddenly, the world woke up to the geopolitical weapon China had quietly forged. The control of rare earths was no longer a simple matter of economics. It was a tool of statecraft, a lever that could be pulled to exert immense pressure on rivals. The era of blissful ignorance was over. The dependency was no longer theoretical. It was a palpable, strategic vulnerability. The 2010 crisis was a wake-up call, a geopolitical fire alarm that blared across the globe. Suddenly, securing a non-Chinese supply of rare earths became a matter of national security for the United States, Europe, Japan, Australia, and other industrial powers. The Great Scramble had begun. It was a frantic, high-stakes race to rediscover old mines, find new deposits, and rebuild entire industries from scratch. This wasn't just about digging rocks out of the ground. It was about reshoring decades of lost knowledge, investing billions in high-risk ventures, and forging new alliances to break the chains of dependency. A new kind of gold rush was on, but this time the treasure was far more complex and strategically vital. The United States, once a world leader, moved to revive its domestic capabilities. The Mountain Pass mine in California, a ghost of its former self, was resurrected under new ownership, with a renewed focus on building out the entire supply chain, from mine to magnet. The U.S. Department of Defense, acutely aware of its vulnerabilities, began funding projects to secure rare earths for its advanced weapon systems, treating the elements with the same strategic importance as fuel or ammunition. It's a slow, arduous process. Rebuilding an industry this complex is like trying to regrow a felled rainforest. It takes time, immense resources, and a steadfast commitment against the lure of cheaper, faster alternatives. Across the Pacific, other nations are making their own moves. Australia, with its significant rare earth deposits, has positioned itself as a key alternative supplier. Companies like Lynas Corporation are now operating a mine in Western Australia and, crucially, a processing plant in Malaysia, providing the world with one of the only viable, large-scale, non-Chinese sources of separated rare earths. Alliances are forming. The Quad nations, the US, Japan, India, and Australia, have explicitly made resilient, rare earth supply chains a cornerstone of their strategic partnership, pooling resources and intelligence to create a united front against market manipulation and supply disruptions. Europe, too, has joined the fray, launching its own raw materials alliance to identify and support mining and processing projects within the continent. Sweden recently announced the discovery of Europe's largest known deposit of rare earth oxides, a promising sign, though it will take more than a decade to bring it online. The global map of rare earth production is slowly, painstakingly being redrawn. It's a geopolitical chess game being played out in mines, laboratories, and boardrooms, from the Australian outback to the Arctic Circle. Every new mine, every processing plant, every strategic alliance is a move to rebalance the board and ensure that the future of technology is not dictated by a single player. While nations scramble to dig new holes in the ground, a quieter, perhaps more profound revolution is taking shape in our laboratories and recycling centers. The most promising new source of rare earths may not be buried deep in the Earth's crust, but sitting in our drawers and landfills. We live in a world of e-waste, a vast, ever-growing urban mine of discarded smartphones, laptops, and hard drives. Each of these devices contains a small but recoverable amount of precious rare earth elements. The challenge, much like with raw ore, is developing efficient and cost-effective ways to extract them. This is where human ingenuity comes into play. Scientists are pioneering new methods to reclaim these elements from the scrap heap. Imagine using custom-engineered bacteria that can selectively latch onto specific rare earth ions, separating them from the electronic sludge. Think of innovative chemical solvents that can dissolve and precipitate out pure neodymium or dysprosium from a mountain of shredded magnets. This isn't science fiction, it's the cutting edge of materials science. Recycling offers a double victory. It reduces our reliance on new mining, which is often environmentally destructive, and it creates a circular economy, turning our waste into a valuable resource. It's a strategy born of both necessity and wisdom. Beyond recycling, another path forward lies in reducing or even eliminating our need for rare earths altogether. The ultimate solution to a supply chain problem is to design your way out of it. Researchers at institutions like the Critical Materials Institute are working tirelessly to discover new materials with similar properties. They are exploring the strange world of manganese-based or iron nitride magnets that might one day rival the power of neodymium magnets. They are developing new electric motor designs that require far less or even zero rare earth content. This quest for alternatives is a powerful driver of fundamental scientific discovery. This two-pronged approach of recycling and substitution represents our best hope for a truly secure and sustainable technological future. It moves us away from a zero-sum game of resource competition and toward a model of innovation and efficiency. Every recycled magnet and every new rare earth-free motor weakens the geopolitical leverage of any single producer. It democratizes access to advanced technology not by controlling the source, but by changing the recipe. This is not just about finding a replacement for terbium. It's about fundamentally rethinking our relationship with the materials that build our world, ensuring that progress doesn't come at an unsustainable cost. We stand at a crossroads, a pivotal moment in our technological civilization. The story of rare earths has forced us to confront uncomfortable truths about the fragility of our interconnected world and the hidden costs of progress. For decades, we chased efficiency and low costs above all else, creating hyper-optimized but brittle supply chains that now represent a profound strategic liability. The global battle for control over these 17 elements is a symptom of a larger challenge. How do we build a future that is not only technologically advanced, but also resilient, equitable, and sustainable? This is more than a contest between nations. It's a test of our collective wisdom. The path forward must be one of diversification and collaboration. No single nation should hold the keys to the future. By fostering a global network of responsible producers, we can create a more stable and predictable market, insulating us all from supply shocks and geopolitical gamesmanship. This requires not only investing in new mines, but also demanding higher standards. We must insist on ethical sourcing, ensuring that the quest for these minerals does not come at the expense of human rights or environmental stewardship. The toxic lakes and devastated landscapes left behind by irresponsible mining are a stark reminder that progress without principle is a hollow victory. Innovation remains our most powerful tool. The push for recycling and substitution isn't just a technical fix, it's a philosophical shift. It is an acknowledgement that the resources of our planet are finite, and that our ingenuity is our only truly infinite resource. By designing systems that are less material-intensive, and by mastering the art of the circular economy, we can decouple technological advancement from raw resource extraction. This is the great cosmic choice before us: continue the old patterns of extraction and conflict, or pioneer a new paradigm of sustainable innovation, where we do more with less. Ultimately, the saga of rare earths is a mirror reflecting our own priorities. Do we see the elements of the earth as spoils to be fought over, or as a shared inheritance to be managed with care and foresight? The stardust that formed our planet, including these rare and powerful elements, connects us all. Our ability to harness them for everything from life-saving medicine to clean energy is a testament to the power of the human mind. The next chapter in this story will be written by the choices we make today. Choices about where we source our materials, how we use them, and what kind of world we want to build with them. The cosmos is watching.